In this series, we explore competing models for what happened at, or even before, the Big Bang. In previous episodes, we've covered Penrose's conformal cyclic cosmology, the Hartle Hawking model, eternal inflation, and many more. But now, as we release a new popular book on the subject, The Battle of the Big Bang, co-authored by Phil Halper and Nyayesh Afshordi, it's time to present a new model of the Big Bang, Holographic Cosmology. Holographic physics was born in the 1970s with a face-off between Stephen Hawking and Jacob Bekenstein. Bekenstein suggested that black holes, like any other object in the universe, must obey the laws of thermodynamics. But this means they would give off heat, which Hawking argued was impossible.
In the beginning, Hawking said that black holes cannot be an analog of thermodynamic objects because they do not radiate. Everything that comes in then gets absorbed and nothing goes out. But then a few years later, he actually did a quantum computation and he found that actually black holes radiate.
Ironically, it was Stephen Hawking who ultimately proved Bekenstein right when he proposed Hawking radiation, as this allows black holes to behave like thermodynamic objects. But a strange property was soon found. The formula established by Hawking and Bekenstein to calculate the entropy of black holes was proportional to the area of the black hole, not the volume.
If you have a bigger object, there is more molecules in it. So, for example, if I have a box of wood or a box of bricks, and if I double the size of the box of brick, then there are twice as many bricks, and then there's twice as much entropy at the same temperature. So you usually think that the amount of entropy, which counts kind of how many bits there is in something or how much disorder you could have, that scales like the volume of an object. At least at the constant density.
The entropy of the black hole must be proportional to the area. And that is unusual. The entropy is a characteristic of disorder. So naturally, it should go like the volume. The more volume you have, the more disorder you can put in.
So holographic principle was inspired by basically this entropy observation or entropy statement that in general relativity, it appears that black holes have entropy that goes as their area. But it's kind of taking that simple statement and running with it, extending it well beyond where it was originally supposed to be. And it's saying that it's not just the black holes, but everything which has gravity in it and quantum mechanics. Then that quote-unquote quantum gravity system, in fact, can be described only as a quantum system without gravity that lives on the boundary.
That's actually where this idea started. So Hooft and Susskind thought about this. And first they said, well, maybe this applies to black holes. Then they realized it probably applies to anything with gravity. And the surface, it doesn't need to be, we don't need to have a black hole which has a surface. You can think of any gravitational system and find a surface in it and project onto it. That's really the holographic principle, that what we think as physics in a volume is actually physics on a surface.
Understanding black hole entropy may provide a path to uniting quantum mechanics with gravity, something thought to be essential to understanding not only black holes, but also the Big Bang.
Holographic principle came by focusing on black holes. So black holes is an object because inside it you have the so-called singularity where the gravitational force goes to infinity. And there you expect that you need both quantum mechanics and general relativity. And then by looking at the loss of the loss of black holes, you find that they behave like hot objects, again, in one dimension less. So this gives a hint that the actual data that you need to describe a theory of quantum gravity is encoded in one dimension less. It's a holographic theory.
With the mass media describing the universe as a hologram, it's worth asking how literally we should take the analogy.
I think the word hologram is at the same time a blessing and a curse. It's a blessing because it brings kind of puts some picture into the idea, but it's a curse because different people mean different things with the same terminology. So the universe as a hologram is different than optical holograms like the ones we have in our credit cards. There is an analogy in the sense that if you have a little hologram in your credit card, it's a two-dimensional surface that encodes a three-dimensional image. In holography as a theory of quantum gravity, you have the theory in three dimensions that describes a four-dimensional universe.
Perhaps the most dramatic realization of the holographic principle came in the 1990s with the so-called Maldacena conjecture. With over 25,000 references, it's become one of the most cited physics papers of all time.
But people knew about the holographic principle for a long time, but they were not able to formulate it as a precise statement. And he formulated as a precise statement by saying that the theory in the volume is a gravitational theory, and the theory on the hologram is a non-gravitational theory. It's a duality, meaning that when the theory on the hologram is far from simple, is very hard to solve, then the theory in the volume is simple, and vice versa.
The Maldacena conjecture was so revolutionary because physicists could use the duality to do calculations that otherwise would have been near impossible.
It showed that two theories were equivalent, one being CFT, or conformal field theory, the other quantum gravity in ADS.
ADS stands for under de Sitter. This is a space-time that is supported by negative cosmological constant. And CFT stands for conformal field theory. This is a theory similar to the theories of electromagnetism and strong force, but has an additional property. It looks the same at all scales. It is conformal.
We don't live in an anti-de Sitter space. The cosmological constant, the dark energy we measure appearing to have positive energy rather than negative. But there still could be lessons, and this is still, a hope. It's not a proven fact, but it's a hope that there are lessons we could learn from this ADS-CFT from studying quantum gravity in negative cosmological constant spaces. Maybe there are lessons we could learn there and then extend it to our universe. This extension is still a leap of faith, but is one that we've done successfully in other places in physics, and we may hope to reproduce it here.
The ADS-CFT correspondence ignited intense interest in physics by offering a tangible holographic dictionary to translate gravitational theories into quantum ones. This breakthrough also propelled Kostas Skenderis on a path that would establish the groundwork for holographic cosmology.
I think shortly after ADS-CFT was proposed, there were works trying to generalize it to de Sitter CFT. So while under de Sitter has negative cosmological constant, de Sitter has a positive one, so it is like the universe that we live. And at least in the beginning, there were a lot of confusing results. Some were in support, some were inconclusive. In the beginning, I was very skeptical myself whether this could work. So I wanted to formulate a no-go theorem. I wanted to prove that it's not possible to be done in the way that it was suggested in the literature. So I started by trying to be as agnostic as possible and to make sure that I'm formulating the problem in a way that doesn't depend on my own prejudices. I was trying to formulate in terms of actual observables. In terms of cosmology, we know that we observe the CMB that comes from the very early universe. So I wanted to see whether these specific observables could possibly be computed holographically. We set out to do a general computation for cosmological observables, and then a general computation in dual quantum field theory, and try to see whether it's any possible match. And what we found, quite surprisingly, is that there was a unique match between the two formulas.
Soon, Skendros's breakthrough would capture the attention of cosmologists.
Remember, I was in fact in this very floor. I saw my friend Robert Brandenberger. I was saying that we were chatting during a conference, and he said, "Oh, I have to go. There is this talk I want to hear about. This is a genuinely new idea." Because this was still the heydays of holographic principle. It was like the first few years that it was introduced. It was taken seriously. But it wasn't yet clear how it could apply to cosmology, given that we don't live in a universe with negative cosmological constant. But that was the first time that I heard this talk, and there were kind of a series of concrete steps that Kostas introduced. So Kostas was basically outlining these steps that were, again, somewhat conjectural and speculative, but the steps that could take us from a toy model that we knew had nothing to do with our universe directly to something that could directly predict what we see in the cosmic microwave background today. And that was, I think, very exciting. And I still think to this day might be the most direct application of holographic principle to the observable world.
How does holographic cosmology differ from the standard Big Bang cosmology described in textbooks?
Holographic cosmology is a new framework. So in use of cosmology, the way we understood it the last 100 years since Einstein was that we have our space-time, which is described by some solution of Einstein equations, which describes the cosmology. And this theory interacts with matter and generates the universe the way we see it. So in order to describe cosmology, we need to give Einstein's theory coupled to matter and then analyze that theory. Now, in holographic cosmology, you do not give this data. You give instead the three-dimensional theory. And then you give a so-called holographic dictionary that tells you how to connect the observables in this three-dimensional theory to observables in 4 dimensions. So then you need to do computations in the three-dimensional theory, use the dictionary, and then this gives you the predictions.
The principle of holography states that a theory of quantum gravity within a volume, the bulk, is exactly equivalent to standard quantum mechanics, lacking gravity, on the boundary of that volume, effectively reducing the dimensions by 1.
Think about boundaries. We usually think about the boundary in a space, like boundary of this room in which I'm sitting in. So the leap of faith that Kostas was advocating for is that instead of a boundary in a space, you should think of a boundary in time. Basically, that was where kind of I got interested and I said, okay, so now maybe I can kind of bring my cosmological expertise and this is an interesting problem for my student, Beth, who was looking for an interesting problem. So it's a radical model of the Big Bang where time doesn't really mean anything or time doesn't exist at some point. But there is this boundary and we define the theory of the Big Bang on this boundary. And that's, so basically we look at the predictions of this quantum theory on that boundary and then match it to the basic fluctuations of cosmic microwave background that we see in the sky.
Afshorty and collaborators looked at the oldest light in the universe, the cosmic microwave background, to compare holographic cosmology with the standard cosmological picture, which asserts that the universe underwent an ultra-rapid period of expansion known as inflation.
They showed that experimental data for fluctuation in the cosmic background, which was famously one of the things that inflation solved perfectly. You look at the same data from the point of view of holographic cosmology, you do a fit, and you find that from the point of view of the fit, they're indistinguishable. There's no theory that is better. And so suddenly you say, whoa, wait a second. One thing that people argued, it's really a big achievement of inflation, suddenly is solved as well by holographic cosmology. So I was blown away by that. And I said, I have to work on this.
Perhaps the most important takeaway from holographic cosmology is that time is emergent. If we travel back to the Big Bang, time would not exist. Time is not fundamental, just like the wetness of water is not found in its individual atoms, but when a large group of them come together under the right conditions. And just like the behavior of water can be described either by a quantum theory specifying the behavior of countless particles, or through hydrodynamics, which averages out particles to treat the fluid as a single entity. So holographic cosmology lets us do the same with time, using a technique known as renormalization group flow.
Renormalization group is basically the idea that, if I'm looking at something, like imagine I'm kind of looking at, there's a crossword puzzle, for example. Okay, so I can look at the look at individual letters, and then I could kind of connect them and then make words, right? But then I can kind of blur my eyes, and then I can see kind of overall shape of, okay, so where are the black places and where are the white places? I could blur my eyes even more and say, okay, so this is a newspaper. There's a crossword puzzle here. There's some kind of pictures on this side, and so on. So you kind of blur your eyes at different levels, and then you see different things, right? Now, in principle, all the information are there in all of these blurring. But when you blur your eyes, you kind of scramble the information on small scales, and then you kind of put your focus on larger scales. So that's the idea of renormalization group, because, we think we experience time, but this quantum theory doesn't have any time. And the idea then is that time really comes from coarse graining, or basically blurring your eyes more and more. So if you blur your eyes more and more, you kind of go to earlier and earlier times in this in the quantum gravity theory. So that's kind of where this renormalization group flow comes from, is that kind of coarse graining or scrambling things on larger and larger scales is like pushing in time backwards.
The renormalization group flow is basically quite simple to understand. If you have some variable, let's say switching on and off something, coloring something with either white or black, and we divide an infinite space into a grid of small squares, and then we want to average. Let's say we want to average over 4 squares to make a bigger square. So then we would define, depending on how many of the squares inside are white and how many are black, whether the bigger square is white or black. So this is sort of an averaging procedure. So this averaging procedure, in the way I described it, goes from small distances, small squares, to big distances, big squares. Holographic cosmology, we have the opposite flow. So bigger and bigger distances, meaning bigger and bigger squares, correspond to the Big Bang, and then smaller and smaller squares, so smaller and smaller distances, correspond to large times.
Time evolution in holographic cosmology is the inverse of that process, this inverse renormalization group flow. And then, so you always have this renormalization group flow, but it's not going to manifest as a big macroscopic direction at all times. You need strong enough interactions, like in the example of the water. You need a large number of them to kind of form a liquid, so that the description in hydrodynamics is useful. Or another example would be temperature. Again, each individual atoms do not have temperature on its own, but if you have a collection of different atoms interacting and reaching equilibrium, then it's more useful to say this is the temperature rather than an enormous number of numbers that describe where each molecule is in this room.
Ultimately, then, the Big Bang happens when the interactions of quantum fields become strong enough. This is the moment that time emerges, the moment when the universe as we know it was born. But if time is not fundamental, then what is?
Fundamental quantities in the holographic universe are the quantum fields in 3 dimensions. And then the space-time and the description in terms of a macroscopic 4-dimensional space-time emerges when these fields interacting strongly with each other.
If time emerges at the Big Bang, does that mean holographic cosmology is a beginning or beginningless cosmology?
This renormalization group flow is defined from a size 0 of squares up to a size infinity of squares. And so if you reverse that, it means, as I said, the Big Bang corresponds to infinite size of squares. So infinite size of squares is mapped, roughly speaking, to time 0. And size 0 of squares is mapped to time infinity. So from that point of view, there is a time 0 and there is a time infinity. So there is a beginning if you call it time 0. Though, of course, calling it a beginning is somewhat cheating because, as I said, things are very fluctuating there.
In my view, the universe existed forever. It is this timeless 3-dimensional theory. It exists forever. What emerges, time emerges at some point. But beyond that, the universe is there forever.
But an alternative view is to say holographic cosmology is a theory of the boundary of the Big Bang, not worrying about what came before.
What if we just refuse to tell the story? And that is kind of the thing that's radical about it and kind of intriguing, maybe not very satisfying, but on the other hand, in some sense, very minimalistic, that it's a story without a story. So why do you care about a story? I guess that's the way I would like to think about it. Maybe we like it because we like a storytelling, or we always like listen to stories. We want to fall asleep, so it gives us this comfort. But really, at the end of it, if you think about it, what we care about is what the outcome of the story. Whatever happened in the past, maybe the only thing we can test about the story is what happened at the end. And holographic cosmology gives you a set of rules for what the end of the story. So what comes out of this story has these properties. But what happened during the story, holographic cosmology says that maybe we just don't care about that, or we just don't tell that part.
Nevertheless, the singularity theorems proven by Penrose and Hawking that were used to prove a beginning of time do look vulnerable to holographic cosmology.
So in classical general relativity, the famous theorems by Hawking and Penrose that says that there's going to be an initial singularity if you go further back in time. And this initial singularity, Einstein equations do not make sense anymore. So any true description of the very early universe, it has to involve a resolution of the singularity. The way this happens in holography is by looking at how the quantum field theory behaves at low and low energies. And the general properties of well-defined quantum field theories is that these are well-defined at arbitrarily low energies. And the mechanism where you see this explicitly is what resolves the initial singularities.
Ultimately, the singularity theorems are classical, meaning they're based on a geometric description of 3 space dimensions and 1 time dimension. But holographic cosmology does away with this to give a truly quantum description of the universe.
And this implies that there's no singularity. This is a very explicit mechanism that resolves the initial singularity and provides finite observables.
The idea that time disappears as we approach the Big Bang is something we've seen before in episode 5 of this series when we examined the Hartle Hawking no-boundary proposal.
I think the Hartle Hawking proposal and holography are very closely related. So I think one can think of this holographic description as describing the initial state that Hartle and Hawking were suggesting. In their language, this was still kind of a geometric picture that they had in their mind. So it can incorporate this geometric picture through holography in terms of some strongly directing three-dimensional theory, but now it allows to extend that proposal to go beyond the geometric picture.
While holographic cosmology could realize the Hartle Hawking model, a key difference then is that in their original proposal, the universe has 4 dimensions throughout its past, even though time turns into space. Holographic cosmology, by contrast, is fundamentally 3-dimensional.
The way to formulate this difference between Hartle Hawking and holographic cosmology is that you go back to t equals 0, you lose time. Time is completely emerging. You have just 3 space directions, whereas in Hartle Hawking, time just changes close to t equals 0. It changes to something like a space direction. You have 4 space directions instead of 3.
With physicists suggesting we live in some analogy of a hologram, it's not surprising this has attracted a range of pseudoscientists hoping to use the new physics to promote their beliefs.
I'm getting a lot of messages from many people that they think that there's some consciousness behind it, and then or maybe metrics and everything. So holography somehow is meant to support these ideas. I do not see any connection myself. I do not see why you need any conscious being. So the emergence comes from interactions in this 3-dimensional quantum system. That doesn't need consciousness to direct.
Another mystery of the Big Bang is why was its entropy so low when high entropy seems more probable? Furthermore, how is it that there is an arrow of time when the basic equations of physics seem to run equally well forward or backwards in time?
One of the properties of normalization group flow is as we go to low energies, we need fewer data to describe the system. So the lower you go, the lower energies, the fewer the data. So if we describe now the information that we need in terms of entropy, the state at the very low energies is very low entropic. And there is also something which is called universality in quantum field theory, which says you can start with the different systems at high energies, but all of them, they're going to go down to universally to specific states at low energies. And as we just said, these are going to be very low entropic. So now if you turn this around, then since normalization group, since time evolution is inverse normalization group flow, this means that we move towards the future is more and more complex, which is also what we observe.
And then you get an arrow of time.
And you get an arrow of time, yes, automatically.
Inverse time goes to, it's like this randomization group flow. So if you keep averaging squares, eventually you average all the way to 1 square, which amounts to 2 states, black or white, or entropy 1. So, and this corresponds to the Big Bang. So averaging all the way corresponds to Big Bang. So entropy of order 1 corresponding to the Big Bang is extremely natural from the point of view of holographic cosmology.
While inflationary cosmology was developed to address several Big Bang mysteries, is holographic cosmology a competing or complementary theory?
So I can think of inflation as a specific holographic cosmology model where the dual quantum field theory has specific features. But you can also think of holographic cosmology as something which is alternative to inflation because also contains models which are the alien universe was non-geometric, do not have an analog in terms of conventional inflationary theories.
You could think about holography as a whole as this, that is it a theory or not? And I think the idea is that really it's a language. So holography is like a dictionary that translates a quantum gravity story to a quantum mechanics story. And sometimes it's not a story, I guess, in our case, it's just what came out of the story. But it's just one story to another story. It doesn't tell you what the story is, and it's up to you to still decide which is the story that you want to have. And inflation is a story for the early universe. It's a very concrete story. I mean, there are some holes in it, but it still is a story. And you could come up with a holographic kind of dual, what kind of holographic theory inflation is dual to. So that's one version of holographic cosmology. It's not a particularly useful version of holographic cosmology because we already have the inflationary story. So we don't really need this alternative story necessarily. You may still want it, but we don't need it. Alternatively, and where it gets more interesting is that maybe there are situations where we don't really have a concrete story of what happened at early times near the Big Bang because it's a deep quantum gravity regime and it's very hard to understand. And we don't have the rules of quantum gravity, but still we want to have a description of what came out of it. And that's where holographic cosmology is useful because we could come up with a set of rules, the theories that are well defined in this quantum mechanical boundary. And that's kind of what we studied. Those theories are easy to understand on the boundary, even though the theory in the bulk, which is basically what happened during quantum gravity Big Bang regime, it's really, we cannot describe that in any comprehensible way.
But if holographic cosmology does become an alternative to inflation, how can it explain the issues inflation is thought to resolve? Let's take one example, the horizon problem.
The horizon problem is the fact that if you look in one direction in the sky, you see something correlated with the fluctuation correlated if you look in the opposite direction in the sky. And yet, the light coming to you from one direction in the sky never touched the light that comes from the other direction in the sky. They come from different places that never interacted. So there was no reason for them to be correlated at all. Now, in inflation, the way this is solved is by saying that the space expands very fast, so things were initially correlated. The way we say it in holographic cosmology is that initially, the initial state was a single state and a state without infinities, and that state was always there and describes always the correlations.
All of the all of the big puzzles of hot Big Bang cosmology have an alternative explanation using holographic cosmologies, and all of them are related to properties of renormalization group flaw. So even the usual explanations provided by inflation, you can also reformulate those exactly in the same language. So you can have a reformulation of the usual resolution of the problems in terms of cosmology, now mapped to properties of renormalization of the properties of the renormalization group flaw. And then in the non-geometric model, we can just use properties of the renormalization group flaws in order to resolve these puzzles.
Holographic cosmology has passed important tests on the road to validation, but there's still a long way to go. So what's the future for this new approach to the Big Bang?
Fitting data is always it's a roller coaster ride, let's say, because you need to kind of work very hard to first understand the data, understand the models. There's a lot of kind of work that goes into that. And then it always involves a lot of trials and errors because, so even when you think you understand things and you compare things, then usually things don't match, right? So, and then you have to kind of go back. So, did we do this right? Is there a bug in my code? And that usually takes months. Generally it does, because it takes time to understand your theory and your data. In the case of holographic cosmology, we have a good understanding of what happened on a small scale. We have nice predictions. But then when you go to larger scales, then we kind of lose track of calculations. Calculations become hard, almost impossible to do. So we knew that going in. We still tried to fit the data. And interestingly, it seemed that like on angles like smaller than 10 degrees, we could on angles smaller than 10 degrees we could fit everything at high precision. But when we went to larger angles, then everything got messy. And people already knew this. Like there are all these like hundreds of papers on weird anomalies on larger angles in cosmic microwave background observations. At the same time, we also knew on the same scales, we don't understand holographic cosmology very well. So then we kind of, when we made this separation between large angles and small angles, and that was kind of the thing that Beth did, and was the new thing. Nobody had done that before. There's this interesting picture image that everything worked very well if you look at the small angles, and large angles, where we don't understand holographic cosmology very well because of this weird quantum mess. The data also doesn't fit well, but also we don't really know what we should be fitting because we don't have good predictive theories on large angles. So that's where things stand right now. I think we are, I know Kostas and his collaborators are working on computer simulations of understanding what happens on these larger scales. In the same way that there are these lattice QCD simulations that we try and understand structure of a proton, for example, based on quarks and gluons. We want to do the same thing with holographic cosmology.
One thing is to try to describe the reheating, which is what happens when we connect to the standard cosmology and our own universe. And I'm working with Kostas on that right now. We have an idea that probably will work out. I think will work out. And also, there's one hope that another thing that we're working together with Kostas is something that people don't usually think of in cosmology. Namely, when they say that we cannot connect with our cosmology, they just mean to get, bosons, bosons and fermions, particles that behave in a certain way. But very few people try to think of how to get the actual standard model of particle physics, the actual content in terms of particles of our own universe. And we think that there's a way to do that. So we're trying to get that. That would be more than what people are doing right now in other types of models.
I think the two things I look forward to is these computer simulations that could tell us more about the quantum properties of these theories on larger scales and whether that's going to address anomalies. And the other one, which I'm also very excited about, is whether we could somehow tie holographic cosmology to dark energy, or maybe its dynamics on larger scales, given that dark energy is more exciting than we thought it would be. And maybe we could somehow tie early universe to late universe, maybe early time inflation or dark energy to late time inflation or dark energy. Maybe there's a way to tie these together in the holographic cosmology framework. So I think these are all directions that kind of are tantalizing, and I think there is potential for exciting discoveries. But which one is going to be the one which will have the big breakthrough? I'm not entirely sure.
I think the dream is to have a holographic theory that describes the entire history of the universe without having to have, because right now what we can describe very well is the very early universe, how the Big Bang happened, what are the observational signatures, maybe try to understand the initial singularity. But eventually we want one theory. We shouldn't have to transition between a purely holographic description at early times and then kind of bulk, kind of conventional description for later. It should be one quantum field theory that describes the entire universe. And then the normalization group flow of that theory should describe the cosmological eras the way we know them: radiation domination, matter domination. You should have something to say about what is dark matter. I think already has something to say about what is dark energy, because one one of the main features of randomization group flaws is that the theory transitions from a so-called one fixed point in very high energies to another fixed point at very low energies. And the descriptions close to the fixed points are kind of universal. They have this property that they look the same at all energy scales. They're so-called conformal field theories. And conformal field theory, now if you see what it means for holography, it means that the bulk space-time has a cosmological constant. So the fact that we see cosmological constant now, that we have an evolution which is driven by dark energy, is a sign that we're close to the fixed point at high energies. And we expect, since the universe should be a transition between the future kind of fixed point at high energies to the past one at low energies. So we can see, and so we can describe the two ends quite well. But the in-between is still a work in progress.
Holographic cosmology has the potential to give us a complete description of the history of the universe and solve some of the biggest puzzles in cosmology. And so far, it fits the cosmological data just as well as the standard model of cosmology. But as new computer simulations are developed, we shall see if it can go further, perhaps revealing whether or not we actually live in a holographic universe.